do is to take a photo of all of you in order to try to remember your name. It's very difficult for me, but we'll try. Okay, smile. Okay. I won't go through all of you right now, but I just want to get some feeling. How many people here study math or physics or computer science or anything like that? Okay. And how many people didn't? Okay, so I think we've covered everyone. Okay. In general, I think as you already know, the computational courses in the ELSEC program are difficult for people who didn't study math and physics, and of course the idea of the program is to try to provide some complementary studies in the beginning, but still it's difficult. It's a difficult course, especially again for students without this kind of background. And this is the second time I'm teaching the course, and I know that all the students in this program are very highly motivated and very smart people. So it's nice to see how people, despite the difficulties, try to manage to learn and to understand the concepts, but be prepared to work hard. Okay, so the first thing I need to say is that the name of the course has changed over the summer. We decided to change the names of Reshatot Aleph and Bet, Neural Networks 1 and 2, to Theoretical and Computational Neuroscience 1 and 2, because we think that some of the topics are not really about neural networks, although many of them are. We think it's just a more correct and more appropriate name for these courses. Okay, you have my name here. I sit physically part of the time in the Ratzach Institute in physics, and part of the time here. So during this semester, I'll usually be there on Sundays and Mondays, and here on Tuesday and Thursday. My office is just around the corner in the corridor over there, so I'm not going to set up a formal reception hour. Please just stop by or check with me. I mean, just stop by if you want to meet. I might say that I can't meet at that moment, but I'll be glad to set up a meeting, and you can also send me an email if you want to meet. Netta Ravit is the teaching assistant. Hours. So the course will be like today, Tuesday 12 to 2, and Thursday, usually what we will do is 12 to 1 will be class. Thursday 1 to 2 will be TA, but we might sometimes change it, so if we do, we'll try to send an announcement in advance. Netta will give an extra hour, especially intended for people who have less background in math. It's not going to be a formal TA hour in which she teaches material, but it will be designed in order to somehow complement and discuss those topics which are difficult for people, especially for people with less mathematical background. Of course, everyone is very welcome to attend, and it's as far as I know, it's going to be on Sunday at 3, but Netta will discuss this with you on Thursday. Note that the Moodle page for the course is on the Moodle 2, not on the Moodle, okay, and it's already open.
About the grade breakdown,
yeah.
Can we change that? So like 30 or 60, 40? Like that much weight on a final exam is really a lot.
It might be that we cannot change it because of some of the regulations of the university. I'm not sure.
I doubt it.
Okay, I don't know. I will discuss this with Netta and maybe, but I don't think that will be a dramatic change. Okay. I think this is what has been done in the past few years in the course, but we'll think about it. Okay. Now, one other thing is that because last week we didn't have classes, we need to make up for that time. So it's 3 hours of teaching and 1 hour of TA. I think the best way to do it is to add 1 hour in the next each week in the next few weeks. And I would like to just now check with you very quickly the options that I think are the most convenient. And if we see that this doesn't work, we'll need to try to do it to do a more elaborate search for other times. So I think the best times are just to put it immediately after the class, either on Tuesday or on Thursday. And I would like to ask if anyone cannot do it on Tuesday from 2 to 3, okay? And is that anyone cannot do it on Thursday from 2 to 3?
Can we just add 1 hour earlier?
I think not. We checked about various limitations, and 1 hour, I will note down the possibility. I mean, okay, so let's just check. Can anyone not do it on Thursday from 11 to 12? Yes, okay, so that's already found it. So for now, we'll
Like,
select.
this will be next week?
So this will, that's a good question, whether we'll start already this week or not. Actually, we should start this week. No reason not to. So, okay, so I will send a message on the Moodle today that the time will be Thursday from 3 to 4, but if some strong objections.
No, it's not long.
Ah,
I have classes in like the rest of the week.
you have classes, okay. So, no one can do both, either one of them, in either one of them, there's someone who cannot do it, so we'll need to check other possibilities. Okay, so by the way, the course will be almost uniquely on the whiteboard today. I'm going to do some, start with some introduction, some concepts, and this will be more or less for the first hour. So, just what I would like to do now, you know what, questions about you. How many people here are not in the LSEC program? Okay, this is what I thought, but good. Okay, so what I would like to do first is just to go over some basic concepts about neurons, about the brain, and also through this discuss some viewpoints which are the way that we're going to view these topics in this course. And I'm sure that you know much of what I will say. Many of you know much of what I will say in this hour. Okay, so what is a neuron? So first of all, a neuron is a living cell, but neurons are very diverse. As you can see in the traces of the morphologies of several neurons, these are just 3 examples. There are many other different morphologies that can be found in the brain. And each neuron has its cell body, so as we mentioned, it's a living cell, and the cell body includes the types of organelles and ingredients that most cells have, including the nucleus. And as you can see, in terms of the spatial extent of the neuron, it's a very small part of most neurons. And then what is very characteristic of neurons is they have these long processes, long and branchy processes. And there are 2 types of processes in most neurons. Like almost every rule in biology, there are exceptions to almost any rule that I will mention. But this is the general rule is that neurons have a process called an axon, which is the output of the neuron. Neurons communicate with each other. We'll talk about that in a moment. So the axon is the output. Axons can be very long. For example, neurons, axons that go through the spinal cord are in order of a meter long. And most neurons have 1 axon, but not all of them. And then neurons have dendrites, or sometimes these are called dendritic trees. Sometimes more than 1, often 2. But these are very, very branchy, as you can see. And these are the source of input to the neuron. And the extent of dendrites is smaller than that of axons. It has to do with the way that the signal, we'll talk about it in a moment, the way the signal propagates in axons and dendrites. In dendrites, the signal cannot propagate very, very long without being attenuated. And therefore, the typical range that a dendrite can span is about 1 millimeter. Okay? But they are often very branchy, as you can see, very diverse in structure. All right, so what is a neuron from our point of view? First of all, this is a computational course, so from our point of view, a neuron is a basic computational unit And as I already mentioned, it receives inputs from other neurons through the dendrites. It sends outputs to other neurons through the axons. And the communication between neurons is mediated through the places where an axon meets a dendrite. And these places are called synapses. Okay? And the neuron receives, okay, so neurons communicate in the form of spikes. We'll talk about that also in more detail in a moment. The neuron receives spikes from other neurons, and somehow in response to the pattern of spikes that it receives, it decides when to emit a spike. Okay. Now, the most important dynamical variable in a neuron is an electrical signal. It's the potential across the membrane of the neuron, the voltage difference between the outside and the inside of the membrane of the neuron. And this changes dynamically because of the flow of ions. Okay, so ions flow through ion channels. They also flow through what are called pumps. Ion pumps maintain constantly a difference in concentration of various ions between the inside and the outside side of the neuron. And it's really, broadly speaking, the dynamics of the membrane potential that determines the electrical activity of the neuron. Okay, so I mentioned spikes, and very roughly speaking, whenever the membrane potential of the neuron goes up beyond a certain threshold, a certain process is initiated. It's a very nonlinear process. What happens is that once the membrane potential becomes sufficiently high, certain ion channels open. Because of that, there's a large flow of ions through the membrane potential continues to increase. At a certain point, some other ion channels open, and this causes a decrease in the membrane potential. So the result is very characteristic and very precisely timed event in which the membrane potential suddenly goes up very quickly and goes down quickly, and eventually it returns to the resting state. Okay? Now, this means that in the language of dynamical systems, the neuron is what we would call an excitable system. And just to give an analogy from everyday life, this is similar to flushing the toilet. Why? Because once we push the button beyond a certain point, there's a certain quick chain of events, right? Water suddenly flows out. Once enough water flows out, it opens up it closes the part through which the water can flow out, and instead it opens, allows flow of water back inside in. So it's a cycle that happens immediately, and it's a cycle that essentially cannot be stopped. And the dynamics here, in some sense, are very similar. Once the membrane potential goes beyond a certain point, there's this chain of events which is very stereotypic, and it's very hard to stop it. And eventually, the neuron goes back to its more or less to its initial state. So this is a very highly stereotyped temporal dynamics, and once this happens, this signal, this perturbation in the electrical state of the neuron propagates along the axon. Okay? And axons are constructed in such a way that it can propagate for a long way. This is why axons can be long. Okay, so there's this electrical signal, and a central dogma of neuroscience that most neuroscience believe, or at least wants to believe, is that the currency of communication in the brain is spikes. And what I mean by that is that it's just the timing of the spike that carries, how many spikes, and the timing of the spike that carries information, but not the shape of the spikes. Okay, so, and this is supported to a large extent by the fact that the shape of the spikes are indeed very, very stereotypical. They change very little. But in principle, you might imagine that in some subtle way, the change of the shape of the spike can vary, and that this carries information. Most research in systems neuroscience, we believe that that's not the case. But it's important to keep in mind that that's an assumption. It's supported by for many reasons, but it's probably not absolutely correct. Okay, so let's talk a little bit about the connection between an axon and a neuron, the synapse. one of the remarkable properties of this form of communication is that, which is the common way in which neurons communicate with each other. There are some other ways. This is that the flow of information from an axon to a dendrite is not electrical, although the signal propagates, the signal that propagates along the axon and along the dendrite is an electrical signal. It's a change in the membrane potential mediated by flow of ions. The communication along the synapse is not electrical, and again, I'm providing here a somewhat simplified description of the process. What happens when the spike reaches the synapse is that these vesicles, which are in the presynaptic side of the axon, these are small membranes which enclose a certain chemical called a neurotransmitter. They exist here. Once the spike reaches the synapse, a certain chain of events starts, and these vesicles fuse to the membrane, and they release the neurotransmitter. Okay? Just to see that this is real, here's an electron microscopy image where you can actually see some vesicles fused to the membrane. Okay? And this neurotransmitter depends on the type of synapse. Okay? There are various kinds of neurotransmitters. You know some of their names. Glutamate, acetylcholine, many others, various others. And on the postsynaptic side, there are receptors. These receptors, when the neurotransmitter reaches these receptors, this causes either directly or indirectly the opening of ion channels on the postsynaptic side. And so now, once the ion channels are open, there is a flow of ions, and the signal is translated again to an electrical signal. Okay, so this is how synapses work. And the most important distinction between different types of synapses is according to the question whether the opening of the ion channel in response to the neurotransmitter causes an increase in the membrane potential, okay, polarization, or a decrease in the membrane potential, hyperpolarization. If it's an increase in the membrane potential, this is an excitatory synapse. It biases this neuron to be more likely to fire spikes. If it's a hyperpolarization, if it decreases the membrane potential, it decreases the probability that this neuron will generate a spike. Okay? And one of the important rules, for which, of course, there are some exceptions, is Dale's principle that tells us that a single neuron either creates excitatory synapses to its postsynaptic partners or creates inhibitory synapses to its postsynaptic partners. Not both. Okay, so neurons are either excitatory or inhibitory. And again, this is a general rule. Okay, so here's the simple view of what a neuron does that we will think of in this course. We will think about it as a computational unit that receives inputs in the form of spikes. Okay. We will assume also that the neuron sums these spikes more or less linearly. We will assume that it's linear. Okay, so the effect on the membrane potential of a neuron is a linear sum over contributions from its presynaptic partners, from the spikes in the presynaptic partners. This is because the propagation of signals on dendrites is to a large extent indeed a linear phenomenon. Okay? But it's important again to remember, this is an assumption, this is a simplification. There are some exceptions. There are cases where there are nonlinear phenomena occurring within the dendrites. We will ignore that. Okay, so a neuron sums up its inputs in a linear fashion with weights that reflects the strength of the synaptic connections between this neuron and its presynaptic partners. So what does the weight really represent biophysically? It represents maybe how many synapses. So the weight of connection between neuron I and J reflects maybe how many synapses there are between neurons I and J, and also the strength of these synapses. What does the strength mean? It means whenever the spikes arrive at the synapse, how much neurotransmitter is released. Maybe also what is the probability that the synapse will actually be activated. so the neuron, our computational view is that the neuron does this sum, and based on this sum of the inputs, it decides whether to send whether to produce a spike. And moreover, in most of what we will do in this course, we will assume that it's not just that the neuron decides when to send the spike, it just decides on the firing rate. Okay, so based on all its inputs, it decides what it's going to be the rate at which it's firing. And so what I want to do now is just to give you a feeling for what are the kind of models that we will work with. Some of you, probably most of you, have seen similar models in Neural Networks 1. But so it's not really very important right now to go into all the details again. This is mainly to give you a feeling. For example, we might imagine the following, that the neuron sums up its inputs. I will explain what is Sj in a moment, but this represents the activity of neuron J. Okay, so the neuron sums the activity of all the neurons Sj with weights. These weights represent the strength of the connection between neuron J and neuron I. Maybe there's some bias here, which could represent either where the threshold of the neuron lies or some external input. So all this sum is what the neuron computes from, neuron I computes from its input. This goes through some nonlinear function, and this sets the firing rate of the neuron. Okay? Why do we need a nonlinear function? Why do we need a nonlinear function?
Spike or no spike, or spike or no spike or multiple spikes?
Well, we're thinking now about really a rate. So it's not even, spike or not spike. The neuron, this sets the, how many spikes per second the neuron generates. So why do we need a nonlinear function? That's a good reason, but there's another fundamental reason why we need to have a nonlinear function here. I'll give you a hint, and that is that the weights, remember, they can be negative and they can be positive. Some of the connections are excitatory and some are inhibitory. I don't know if this helps, but you can also look at this example for a nonlinearity.
You can't have negative spikes.
Okay, we cannot have a negative rate, right? So if this is going to represent a firing rate on the right-hand side, it cannot be negative. And so if we construct a model of a neural network that has only excitatory connections, no problem. Everything here is positive, and we could work with a model in which it's linear. And in fact, some neurons are quite linear in the response. But once we have inhibitory connections, and in most models of neural dynamics, it's really important to have inhibitory connections because otherwise activity just blows up. Then sometimes the sum will be negative, okay, and sometimes it will be positive, and you cannot imagine that the firing rate can become negative. So this is the most simple nonlinearity that we can think of, that the neuron fires at a rate which is proportional to its input as long as the input is positive, but if the input is negative, the rate is zero. Now, negative and positive sounds like a bit arbitrary, but it's really this parameter here that determines where in the regime of input the neuron starts to fire. Okay, so this is a simple model of neural dynamics, but what I didn't tell you yet is what is Sj. So you might imagine that Sj is simply Rj. Okay, I mentioned that Sj represents the activity of neuron J, but we usually assume that it's a bit more complicated. The reason is that before I write the equation on the right-hand side, what really you see here is the effect of neuron J on neuron I. And the effect of neuron J on neuron I goes through the synaptic connection, right? Now, whenever something changes in the input to the synapse doesn't react immediately. There is a certain characteristic time scale for the response of the synapse. If we backtrack a little bit and instead of thinking of rates, think of spikes, when a spike reaches a synapse, this causes opening of ion channels, this causes a flow of ions, change in the membrane potential, and all this happens over a certain time scale. What is the time scale? It depends on the synapse. It can be 10 milliseconds. For some synapses, it can be a few milliseconds. For others, it can be up to about 100 milliseconds for NMDA synapses. So what we want to model here is that Sj is not exactly Rj, but it's a certain kind of smeared a version of RJ which is smeared in time. And this can be expressed mathematically by using this equation, which tells us that the Fj really depends on Rj. Okay? And actually, I should have put this on this slide, but I will write on the whiteboard. If we would imagine that Rj is a spike, and we would solve this equation, what the result that we would get is that Fj looks like this. It starts immediately after the spike, and then there's a gradual, graceful decrease in Sj over a time scale, which is exponential. And the time scale is this tau that you see in the equation. So the differential equation that you see on the right-hand side is really another way of writing the fact that the response to a change in the input in the spike rate is translated into a change of the synaptic activity, which has this exponential form. And if we would have more than one spike, then maybe I'll draw this in different color. If you would have more than one spike, then the Fj would be a sum over all these contributions. Okay? In fact, in many of the topics that we will deal with in this course, we will work with even more simple models of neural dynamics. And in one topic, we will work with a slightly more complicated model of neural dynamics. But this is more or less the way we're going to think about neural activity. And so if we start from these equations and we just plug in the relationship between S and R, we get this kind of dynamic equation for the S variables. Okay? And just as one possible thing to ask about these dynamics is what happens if we just provide some constant inputs Vi and look for what is the activity in the neural network at steady state. So at steady state, this is going to be 0. And therefore, the neural dynamics, as you can see from here, Fj is going to be equal to Rj, because at steady state this is 0. And then we could write, and then the steady state firing rates will obey this set of equations. Okay, now I'd like to shift attention to a different question that will be relevant also for what we will do in the next hour. And this is, what does a spike in the brain represent? So we stick an electrode in the brain, and we, say, encounter spiking activity of a single neuron, and we observe the spiking activity. What do spikes represent? So one of the important concepts to mention is that of a tuning curve. The concept of a tuning curve arises naturally because of the way electrophysiologists do experiments. Okay, this is an example from the very famous experiments of Hubel and Wiesel, which have led, among other results, to the receipt of the Nobel Prize by them. And what Hubel and Wiesel did is that they stuck electrodes in the visual cortex of animals. And for a while, they had a very hard time understanding what causes a particular neuron to fire. But at a certain point, they realized that if they show to the animal, this is an anesthetized animal, they show to the animal a bar in a particular position in the visual scene, then a neuron that they record with will start to respond very vigorously if the bar is oriented in a particular direction. So in a particular type of cell, a simple cell in the primary visual cortex, one might see the following example. So this is really not just a bar, it's also a bar which is moving, okay? And if the bar is oriented in this direction, the neuron does not respond. If it's oriented in this direction, it responds a little bit. If it's oriented in this direction, the neuron starts firing very, very vigorously. And so you can plot what is the firing rate of the neuron as a function of the orientation of the bar. Okay? So this is called the tuning curve. And one one way to interpret this tuning curve, which is a bit simplistic, is to say, okay, the neuron is representing the orientation of the bar, but of course in most situations the animal is not observing bars and the neuron is representing various other things. But it is true that if we provide this type of stimulus which is characterized by one-dimensional variable, the orientation of the bar, we can see that the response depends on that orientation. Here's another example of a tuning curve in a completely different type of brain area. So this is a sensory, the last example is sensory. The right example is the other periphery of the brain, it's the motor part, the part where the brain generates some output to the muscles, motor cortex. And also very, very influential and important studies by Georgopoulos. Observed what happens when a monkey is trained to move the hands in different directions. Okay? And the observation was that many neurons in the motor cortex have a firing rate which depends on the orientation at which the hand is being moved. So you can, again, in an oversimplistic way, say the neuron is representing the direction of the hand. But of course, it's representing the direction of the hand in an experiment where the only variable is the direction of the hand. Okay? There are some other examples. Actually, I see that I don't have slides for this, but there are some examples where we really can more, I think, with more confidence say that we can measure a tuning curve as a function of a one-dimensional variable, and this is really, in some sense, the one variable which is represented by the neuron. Do you know of an example? Anyone heard of an example of that type? Okay, actually that's not a good example, and I'll explain why. So the Jennifer Aniston cell is an example of observations in the hippocampus, measurements done in epileptic patients in which the electrodes were inserted into the brain for clinical reasons, and as a bonus, people can use this to do some basic science. So it turns out that there are some cells in the hippocampus that fire if the experimentalist mentions Jennifer Aniston or shows a picture of Jennifer Aniston or shows the words Jennifer Aniston being written. So in some sense this is a good example because then it really, this neuron seems to respond very specifically to this concept, but it's quite clear that this neuron will also fire in response to other concepts. Okay? I was thinking about something else, also in the hippocampus actually. Places, okay? But now that we're thinking about it, places indeed are, okay, so first of all, what are places? Places fire in response to the position of the animal, okay? And many cells in the hippocampus have this property. You put an animal in an environment, it's stable, it runs around, and you see that the cell fires only in particular positions. So we could plot the tuning curve. In this case, it will be a two-dimensional plot, as a function of a two-dimensional variable. What is the firing rate of the neuron as a function of the position of the animal? It really seems like the hippocampus is engaged in representing the position of the animal. The same reservation that I raised about concept cells, I think, is correct also for places, because just probably the same cells in the hippocampus are also taking part in encoding other things, maybe concepts, if you will. But there's another related example, head erection cells in rodents. So in other brain areas, you can find cells that fire as a function of the direction of the head of the animal relative to its environment. Again, tuning curves that look very much like this one, and a bit more, it's very much like this one. Certain firing rate, for a particular cell will fire only if the head direction is in a particular direction, and these brain areas seem really their role seems to be to represent the direction of the head, also maybe to update it in response to motion. Anyway, so this is the concept of a tuning curve. Now, again, this is a little bit artificial still in the sense that, for example, when we look at V1, we characterize the response of a particular neuron in response to a very specific set of stimuli, a one-dimensional set of stimuli. how can we discuss what a neuron is doing in response to a more rich, multidimensional input? So let's think of, for example, about the retina. The retina receives a very highly dimensional input, right? You can think about the inputs to the retina as the activation of all the photoreceptors in the retina. And we can ask for a cell in the retina which sends information to the brain. These are called ganglion cells. So the retina has 3 layers of cells: photoreceptors, another intermediate layer, and ganglion cells. The ganglion cells send spikes to the brain. This is all the brain knows about the visual signal, the spike. Everything the brain knows comes from the spikes sent by the ganglion cell. And we can look at a particular ganglion cell and ask, what does a spike in the ganglion cell represent, or how does the ganglion cell activity represent the visual scene? So the basic observation which we will discuss later in the course is that ganglion cells in the retina are activated. A particular ganglion cell is activated by light falling in some particular region in the visual scene, and there's a certain, if we talk about one type of ganglion cell, an on-center cell, the cell will fire more vigorously if there's light falling in this region in the visual scene, but then light falling in some surrounding region inhibits the cell. Okay, so this is a very qualitative description of what the ganglion cell does, and this area in which the cell responds is often called the receptive field of the cell. Okay, so the cell, this particular cell, is receptive to what it responds to what's happening in the visual scene in this area. We say that this receptive field has a center-surround structure, center and surround. But if you want to describe this more quantitatively, we might work with the following simple model of what the ganglion cell does. We might say that the ganglion cell has a firing rate which depends on the input. The input is a function of x. It's a very high-dimensional function. It's the illumination as a function of or light intensity as a function of x. This intensity is multiplied by some function which is positive here, negative here. It has some structure. Okay, and this integral is really what determines the firing rate of the cell through some nonlinearity. So this is a simple model of what the ganglion cell does. It's not a bad model. We will talk later in the course about the question, why do receptive fields of ganglion cells have this structure? Before I summarize this part, I just want to mention that, as I said, in most of this course we will talk about the activity of a cell is determined by its firing rate. I wrote this here. I wrote this also before. This is related to a very important question in computational neuroscience. Is the communication in the brain just mediated by the rate of spikes, or is the precise timing of spikes important? This is a very important question. We will not touch on it very deeply in this course. Most of the time we work with models in which the communication, the activity of the information is carried by the firing rate and not by the specific timing of spikes. Okay, so this is just a summary of the concepts that I reviewed so far: neurons, dendrites, axons, synapse, spikes. I didn't mention that spikes are also called action potentials, rate models, tuning curves, receptive fields. This is a good time to take a break. So we'll take a 15-minute break. בסדר, לא נורא. זה נכון.
ואני כאן נוכח בקורס
יש
של
גם
כל הדברים.
אתה נרשם לדוקטורט בפיזיקה או
במדעי המוח.
במדעי המוח?
כן.
תגיד גם תמיד.
כן, וזהו, ברשמית לא עשיתי את הדברים האלה.
אני לא חושב שזה בעיה, במיוחד...
כן, לא, עברתי כבר על כל החומר.
כן, כן, גם בגלל שאתה בא
זה כאילו
מרקע
כלכלני, ככה
פיזיקלי, מתמטי, אז
טוב, כאילו, טכנית זה כנראה לא שווה אישור.
כן, כן, אבל האמת שהחומר בפני הקורסים הוא לא ממש מוכנות.
לא, אני גם יודע, אתה יודע. גם למדתי כאילו את
אני חושבת שהדרגה שאנחנו נקבל היא...
טוב, תודה רבה.
עדי, כמה אתם שומעים על שלכם? כמה שמנסות יותר מפרט המערכת? אז רק גם הסמורטות? למה? כי יש כאלה שממש במשרד הכלכלה בגלל זה, אתה לא חושב פה מה... אז רגע, כמה זה?
זה תלוי בגיל. כאילו, תינוק פיזי זה 2,300 בערך.
זה יותר. לא, עם אנשים.
אז זה תלוי
כל אחד מדבר על משהו זה.
ההנחה המקסימלית,
700 שקל, זהו.
אבל קיבלתי את ההנחה המקסימלית, אצלי זה ראשון.
כן, כן. אנחנו
עכשיו אני לא מקבלת את ההנחה המקסימלית, אבל היא גדולה הרבה יותר, גם ככה.
כאילו, מה שאנחנו לא קיבלנו, אבל אם באתי נכון, זה 1,700 עם שני מורדפים את המלגה המקסימלית, וזה יכול להגיע ל-1,300 אם לא היינו מצליחים על המלגה של ניר, ובאופן כללי, כאילו מישהי שעשתה איתי ראשונה שנה שעברה, שניהם מקבלים מלגה, והם לא מצליחים על המלגות, וכאילו המלגות משלמות זה, ואנחנו חשובים נורא על זה, בסופו של מלגה האלה. אבל כן, אני מפחדת פשוט, אבל...
אני גם, מספיק שפעם אחת...
לא, היא אמרה ש...
למה אני מצהירה על המלגה? לא, אני מצהירה על המלגה שלי, אבל גם היה לו עבודה, שהוא לא יהיה בטוח שהוא מקבל אותה, אבל לא. אז שלא מעדכנים אותם אחרי זה במשקע שלי.
ממש הם 600,000, 6. אבל מה שאני אוהבת, זה נורא תלוי באופי, כאילו יש משהו שלנו קטן, אני דווקא אוהבת את זה שיש שם סך הכל בתוך הגן שלו יש 4 פלוט, אז זה כאילו, במחלק יש 5, כאילו מקסימום 24 ילדים, אבל כל המשחק יותר באותו גיל, יש שם חצר ענקית כזאת עם מלא משחקים וזה, אבל יש עוד גן של גיל הזה, טיפה יותר גדולים, זה כאילו מקום ענק, המקום עצמו ויטו הוא מקום ענק, יש לנו שזה נורא מוטיע אותם. לטנטן זה כיף. הוא אוהב קטן. אז זהו, זה נורא עניין של אופי, כי טנטן מאוד אוהב, כאילו... למה ההורים שלו אוהבים ואני
Okay, I was reminded that I should record the talks. So first hour, unfortunately, maybe recorded, but without my voice. And it has come to my attention at the break that I think there was some misunderstanding about my question about extra hour, and apparently, I just want to verify, Thursday 3 to 4 is okay. So, does anyone object to Thursday from 3 to 4?
Just for this Thursday.
Just for what?
Just this Thursday.
Just this Thursday there is a problem? There is a problem this Thursday. From next Thursday there is, does anybody object for 3 to 4? Sorry, 2 to 3. 2 to 3. No problem for anyone. Thursdays 2 to 3. Okay, so I will send a message about this today and probably will start already this week.
This is Neta's extra hour?
No, this is my extra hour to compensate for the first week.
And Neta's extra?
Yes. You have a problem this week? Okay, so I will send a message about this and we'll start next week. And for Neta's extra hour, as I mentioned to someone, you should discuss this with her. But even if you find some other time with her, but Thursday, I think it's the most convenient to just stick it to other hours. So if you want to, you can ask her after I finish my, ashlama, to move it to Thursday. Okay. I see that this presentation is going a bit more slowly than I anticipated, but that's okay. So what I want to discuss a little bit is some perspective on computations in the brain. So the area of research that we are working in, that I'm working in, and many people at ELSEC are working in, is called computational neuroscience, חישוביות עצבית, and this term can be interpreted in two ways. The words, especially the English version of this term, computational neuroscience, can be interpreted in two ways, and often is interpreted in two ways. There's one interpretation which I don't like, and it's not how I use this term, which is using computational tools to study the brain. Okay, using math and physics and computer science to study the brain. This puts the computational part as a technique, okay, as a tool. The other meaning, which is much more profound, and this is what I mean when I say computational neuroscience, it's what also the Hebrew translation is like that, is studying the brain from a computational perspective, trying to understand how the brain performs computations. Okay? And most of us believe that most computations in the brain are not achieved by the activity of a single neuron. Computations in the brain are achieved through a collective behavior of many, many neurons, and for that reason, computational neuroscience is often, not always, often focused on the systems level, at the level, at least of the level of a neural circuit. Okay, a collection of many neurons, sometimes a higher level. Okay, so since we want to talk about different levels of studying the brain, also to understand why this is a challenging problem, I want to talk a little bit about the scales in the brain, starting with length scale. So the central nervous system includes our brain and the spinal cord. Is length scale is therefore in the human body is for order of 1 meter. If we focus on the brain and more specifically on the cortex, which is responsible for many of the higher level functions of the brain, then the cortex can be roughly divided into two areas, as you see here in these colors. So the scale is now, 10 centimeters, and these areas are very broadly responsible for different types of functions. For example, this very large part of the brain which deals with vision, another part of the brain which deals with other sensory modalities, this part of the brain which is related to speech, to reading, and the frontal part of the brain which is related to various higher cognitive functions. Now, if we look a bit more in detail on different parts of the cortex, it's possible to identify more specific areas which often have are implicated as as taking part in specific functions. So we started from 1 meter, and then I would say that a little bit hand waving that there are these areas of order of magnitude of 10 centimeters, which I will call systems, and then another important scale, length scale in the cortex, is of order 1 centimeter, because on that scale you can often find a particular area in the cortex which really does one thing. What do I mean by that? For example, in the visual cortex, you might find that if you look, there's a V1 or V2 or V4, there's a complete map of the whole visual scene over a range of neurons which spans about that scale, and another map of the whole visual scene in some other part of the visual cortex, and maybe another map of the whole visual scene. So this is what I mean by map. In a motor area, this could be an area that, if you go through all this area, you will see neurons that activate muscles in the whole body. And then so we went down to the scale of 1 centimeter. Let's go one order of magnitude smaller. So maps is centimeters, maybe 1-2 orders of magnitude smaller, to local networks. A very important length scale in the cortex is the length scale of about 1 millimeter. Now, I remind you that 1 millimeter is also fundamentally an important scale for neurons, because that's more or less the range that the dendritic, that the dendrite can span. And people talk about cortical columns. Now, I didn't mention much about the cortex. I'm sure that most of you know, but maybe not all of you, that the cortex is a layered structure, okay? So we should think about it as a two-dimensional layered structure. And within this layer, people talk about a scale of about 1 millimeter squared, okay? This is a column. And this is often thought of as a basic computational unit in the cortex. Why? For several reasons. One is that connectivity between neurons is often much more dense within the range of that column compared to connections between the neurons that are further away, okay? And the other reason is that often, not always, one can identify that within that range, all the neurons have a similar function or a similar response or a similar relation to external variables. So, for example, in the visual cortex of some animals, cats, humans, all the neurons within the cortical column might respond to a bar in a particular direction, and then in another column they will respond to a bar in a different direction. Okay, so we talked about local networks, circuits, but more generally, this is often when we talk about neural circuits, some collection of neurons that are collectively doing some computation. We think about, we might think about that scale. Neurons themselves are 10 to 100 microns. This is a cell body. The processes, dendrites and axons, can be much longer. And then we continue to zoom in, and synapses, the length scale is about 1 micron. Molecules that constitute synapses, proteins, and so on. Typical length scales could be 1 nanometer. This is an example of a single ion channel. It's composed of several proteins, but its characteristic size is of a few nanometers. So I just reverse the order here. You'll see that if we want to, in principle, we want to understand what the brain is doing, we need to span scales, at least on the molecular scale, 1 nanometer, to the scale of the whole nervous system, which is 1 meter. So we have here 9 orders of magnitude. There are also very, very large scale of time scales in the brain. Okay, an action potential is perhaps, from the point of view of thinking about spikes, perhaps that's the shortest time scale that we should think about. It's about 1 millisecond, but of course there are other time scales which are related to the activity of the ion channels and the synapses, which are shorter. I didn't mention them, but let's start from the 1 millisecond time scale. Membrane integration time, that's the time scale over which the potential of the membrane changes. What do I mean by that? If we create some electrical perturbation on the membrane potential, so So suppose that we inject current for a very brief time in the memory potential, then the memory potential will maybe increase, but then it will gradually decrease to its resting state over a time scale of a few milliseconds. I wrote here orders of magnitude. The memory time constant for neurons is typically shorter than 10 milliseconds. It's a few milliseconds. There's another important time scale which I already mentioned earlier and explicitly modeled in the rate model that I wrote before. This is a synaptic integration time. What do I mean by that? When a synapse is activated, what is the time scale over which there is an effect on the membrane potential through a current, ionic current, an effect on the membrane potential of the postsynaptic neuron? So this ranges from a few milliseconds to 100 milliseconds depending on the type of synapse. Now, these are time scales that are related to the activity. But now we know that the brain is constantly changing, right? So what kind of changes occur in the brain? One is what is called short-term synaptic plasticity. A synapse, when it's activated, will not be as easy to activate maybe immediately afterwards. So there is a certain time scale over which the activity, the ability of a synapse to be activated depends on the history. And that sets a time scale of maybe could start from 0.1 second up to a few seconds. Okay, so this is the characteristic time for short-term synaptic plasticity. But then there are long-term changes in synapses. We believe that long-term changes in synapses and in the connections between neurons underlie much of what we can do. Our ability to learn and also the way that the brain wires up as we develop, as the brain develops, has to do with long-term changes in synapses. So long-term synaptic plasticity occurs over much longer time scales than these, starting maybe from 1 second up to an hour, okay? And then it can last, the effect of long-term synaptic plasticity can last over our whole lives, right? We remember something, some event happens, and we remember it throughout our whole life. So again, you see here that we have many, many orders of magnitude for processes that occur in the brain. Now in the time domain. Let's talk a little bit about numbers. How many neurons are in the brain? So we'll start from one of the most simple animals that biologists study, C. elegans, this nematode, this worm. It has altogether 300 neurons. Okay, so with these 300 neurons, it can move around in its environment, respond to external stimuli, even learn. Again, it has 5,000 synapses. If we move to the next favorite organism of biologists, the fruit fly, Drosophila, we're up in about 2 orders of magnitude, right? 10 to the 5, 100,000 neurons, and 10 million synapses. Moving forward to the mouse, another 3 orders of magnitude. Okay, the mouse is already similar to us. It has a cortex. 100 million neurons. Moving from the mouse to us, another 3 orders of magnitude. Okay, so 10 to the 11 neurons. And if we focus on the cortex has about includes about a fifth of the neurons in our brain. So it's 2 times 10 to the 10. And I mentioned earlier, so now I'm actually zooming in again. I mentioned earlier the cortical column. So the number of neurons that we should think of in the context of the human brain is about 10,000 neurons for a cortical column and about 10 to 100 million synapses. For a mouse, maybe 1 order of magnitude less. Okay, so I mentioned all these vast scales of magnitude in length, in time, and also in the number of neurons in order to highlight the fact that this is a big challenge. This is a cause for a big challenge. We need to understand, or at least most of us believe that to understand what the brain is doing, we need to understand the collective behavior of many, many, many neurons. It's not only that there are many neurons, but there is structure in the system over a vast range of scales, time scales and next scales. And there is a complicated structure occurring on all scales. And this raises constantly difficult problems, which are fundamental problems in computational neuroscience, and you will hear different points of view and different ways to tackle this problem from different people, often people coming from different disciplines. What is the correct level of description for such a system? Do we need to model all the details at the most small scale in order to understand, and in a very detailed manner in order to understand the collective behavior? Or perhaps we don't need always to understand all the small details in order to understand the collective behavior. Okay? What is the level of description that is needed? Do we need to write, when we write equations that describe neural dynamics, do we need to describe the dynamics of each ionic channel, take into account a very detailed structure of the dendritic tree of each neuron? Or can we, in some contexts, work with models which are more simplified, like the ones that I described to you before? And I think there's no one answer to this question. It also depends a lot on what are the questions that you want to tackle, but it's always a big question in computational neuroscience. But the fact that we need to understand the collective dynamics of many computational units is reminiscent of something that is done in other fields of science. And this is really the reason why my initial training is in physics, why I'm talking to you about the brain, because it's somewhat reminiscent of something that we do all the time in physics. In physics, we also need to understand systems that include an extremely large number of degrees of freedom and to understand how they behave collectively. And therefore, the physics provides one point of view which is sometimes useful for understanding the brain. There's one very important difference, I think, between physical systems and biological systems in general, not just the brain, and this is function. Biological systems have evolved to achieve certain functions, and evolution had the opportunity, was able to tweak the structure of these systems at all the different scales in order to achieve the functions. And evolution doesn't care if a certain solution is achieved by tweaking the properties of an ion channel or by tweaking the large-scale connectivity in the brain. Evolution cares only about the function that the brain achieves. So I think this is one of the reasons that biological systems are really difficult to understand collectively. It's the fact that evolution has tweaked structure on all these different scales, and there are often also very complicated connections between the dynamics at one scale and at a much larger scale. Okay? And if we talk about the brain, then the main function that we should think of is that of computation and processing of information. So what are some of the computations that the brain does? Here's just a kind of a list that I came up with very, very quickly. Of course, sensory perception. We constantly measure a huge amount of inputs through our different senses and process them in order to achieve some tasks. Recognize objects, say in the visual scene or in an auditory scene, discrimination between different objects. We make decisions, right? The decisions need to affect something that we do in the world, and this is through motor output. We need to learn something about our environment, about the world, in order to be able to make better decisions, and that's why we have memory and learning. And of course, we can go on and talk about higher cognitive functions, language, creativity, and so on. And so if you look at this list, it's quite clear that in every one of these tasks that our brain does, information plays a very central role. Both in just representing, how does our brain represent information? Okay, both in extracting parts of the information that's coming from the senses which is relevant to us, maybe some parts of the information that falls on our retina or no, cochlea is not important and we can discard it. So we need to extract information which is more relevant and maybe discard information which is less relevant. Our brain communicates huge amounts of information between different brain areas, okay? And it stores information in memory. Okay, so I want to say a few words about the term learning because it's used in different ways in neuroscience. One way in which the word learning is used is from a very mechanistic point of view. People call any process that involve long-term changes, structural changes in the brain, and mainly changes in synaptic connectivity. People call that learning. Okay, but this is a very mechanistic point of view again. The strength of the synapse changes. We call that learning. But the reason we call this learning is that we believe that this underlies learning in the other sense, which is learning something about the world. And when we talk about this other sense, from the functional point of view of learning, there is one very important distinction that I would like to make, which will be an important distinction in this course as well, and that is between supervised and unsupervised learning. So what is unsupervised learning? Unsupervised learning is just learning something about the statistics of the world, of the properties of the world, without any instructor that tells you what it is really that you should learn. Okay? So we might learn various aspects of the world, and this can be it's obviously true in some contexts. It's also, many people believe that this underlies in a very fundamental way the way that we process sensory information, that our brain learns something about the statistics of sensory information and makes use of this in order to represent this information better. We'll talk about that a lot in the course. And then supervised learning, in its extreme case, is a situation where someone is giving you some reward or some answers as to whether a certain answer that you come up with is correct or not. So we were shown some examples. Suppose that you want to categorize, I don't know, cats and dogs. Okay, so unsupervised learning would be that I would show you many pictures of cats and dogs, and you would, after you've never seen these animals, and you would realize for yourselves that there are two different types of animals here, and you will categorize them correctly. Supervised learning would be a situation where I would show you pictures of cats and dogs, and it will show you, this is a cat, this is a cat, this is a dog, this is a cat, this is a dog, okay? Some of the assumptions that we will make, or the points of view that we will take in this course. So in this course, we will think about individual neurons as simple objects. We will not model the dendritic structure of the various compartments of a neuron and its spatial structure and so on. We'll think of a neuron as a simple object, as I alluded to previously, and we will take the point of view that the interesting properties of computation in the brain arise from the collective behavior of many neurons. Of course, this is a simplified view. We should remember that that's the case, but that's the point of view that we will take in this course. And another important assumption, which is many people believe it, and most of us believe is true, is that learning in the brain is achieved through changes in the synaptic connectivity. As I mentioned, we will work with this kind of often this type of models for neural dynamics, mostly rate models, not without thinking about the timing of spikes very carefully. In many cases also, we will consider these dynamics in their steady state, in a situation where there's maybe some input to the neural networks and it generates a certain outputs. And in some parts of the course, we will also deal with dynamics of synapses. And I wrote here kind of a broad description of how we will think about what determines the change in a synapse. We don't need to understand very deeply what is written here, but I will go through the ingredients just to give you a feeling. So we will often think about the change in the synapse from neuron I to J to be dependent on various quantities. First of all, the synapse itself, and then the activity of the presynaptic neuron, the activity of the postsynaptic neuron. We might care only about the rates. In some cases, we might care more specifically about the timing of the spikes in the presynaptic and the postsynaptic neuron. Maybe some reward signal if we're thinking about supervised learning. Biophysically, what could be a reward signal? Right, and so neuromodulators, like dopamine. And maybe some other local variables. But because we want to take a mechanistic point of view for changes in synaptic, for learning, typically the rules that we will write for change in a synapse are local rules. This change in a synapse depends on itself. It depends on the presynaptic neuron. It depends on the postsynaptic neuron. It does not depend directly on the activity of other neurons in the brain. Indirectly, yes, because the other neurons are affecting the activity of the neurons I and J. But there is going to be some local rule. And one of the things that we will try to understand is how do local learning rules shape the structure of a neural network such that it achieves a certain function. Okay, so far this was a very broad overview, and part of what I told you is not necessarily directly related to specific topics in the course. It was one of the goals was to give you a broader description of how I view computational neuroscience. And now I'd like to talk about more specifically about some of the topics in the course. So one area that we will discuss in the course is a very central area, maybe half of the course, is neural coding and decoding. If we have a certain set of neurons that are representing some variables, they have tuning curves or receptive fields and so on, what are the limitations which are posed by the way that neurons represent information on the ability to read out variables of the activity? In some sense, we want to understand what is the fidelity or the precision in which activity in the brain represents various variables, such as sensory variables, perhaps other variables. Sensory variables is very clear, but you can think of other examples, like we discussed place cells earlier. So position of the animal. How well is the position of the animal represented by the activity of neurons in the brain, in the hippocampus? Related to this question, how do we characterize the neural representation? How do we characterize receptive fields, tuning curves, and so on? And then a deep question that we will discuss a lot is, are there computational principles that explain why the representation in the brain looks in the way it has a structure that it has? So, for example, I mentioned to you that in the retina, receptive fields have a center surround structure, right? A particular ganglion cell responds to activity in a particular position, but inhibited by the surround. Is there a fundamental computational reason why the retina represents information in this way? Of course, as you can imagine, if I'm raising the question, I believe that the answer is yes, and we will discuss that a lot. And are there some optimizations? Going even further, can the detailed structure of the representation be explained by some optimization principles that the brain is trying to optimize something? Given that the answer for this will also be yes, that we will raise the hypothesis that the brain, the representation in the brain are optimizing something, we will want to understand whether there are some learning rules, local learning rules, like the one that I described earlier for synapses, that can lead the neural network to achieve a representation which is optimized in this sense. So this leads us to learning. We'll talk quite a lot about learning in this course, and this is one of the main differences with respect to Neural Networks 1 or Computational Theoretical Neuroscience 1, which dealt more with dynamics of neural network. We will deal a lot with processes in which the strength of synapses changes. We want to understand how biologically realistic rules for changing a synapse affect the structure of a neural network. But also, okay, so before this is really not, this item is not really learning. It's asking given that we have particular simple models for what neurons do and how neural dynamics look like, what are the kind of computations that can actually be achieved? But then after we discuss that, we will want to understand how these computations, the ability to perform these computations can be learned. Okay, and these questions will mostly be, we'll discuss them in the context of supervised learning. So we want to learn, say, something like a discrimination task. We're shown many different examples of inputs, and we need to be able to discriminate between two classes. And we have a teaching signal that tells us at each case which of the two examples is being shown. And we want to ask whether we can think of local learning rules in a neural network that receives the inputs, receives, say, in the form of dopamine, an instructing signal, and this neural network needs to arrange in such a way that in the end it will generate an output that, given the input, will say whether it's cats or dogs. Okay? And the question that I wrote here is related more to unsupervised learning and to the topics that I discussed earlier also for neural representation in the brain, because we want to understand whether these neural representations can arise from unsupervised learning. Right, when I am going back now to the previous slide, we're going to raise the hypothesis that the representation of sensory variables in the brain is optimizing something, and now the way that these representation arrive in the brain through development, we will hypothesize or ask whether there are some unsupervised learning rules that can lead a neural network that receives many input to process this information in such a way that achieves these optimization principles. Okay, so given what I've told you so far, some of the main themes in this course are going to be neural coding and decoding. How does the brain encode and decode information? Learning. There's going to be little discussion on network dynamics as opposed to neural networks 1. There will be some discussion on dynamics at the level of synaptic inputs, synaptic weights. And we will want to think about neural networks as computational devices. Often we will think about them as a neural network is receiving some input, generating some output, and we want to understand how it can rearrange, or how the synaptic weights can be arranged such that it achieves a certain function. One other point that I did not raise explicitly so far is noise. Noise is going to be very important in almost everything that we will discuss in this course. When we talk about neural representation, how well neural activity represents information, this question becomes meaningful only if we take into account variability. Because if a neuron has a certain tuning curve, it fires at a certain rate as a function of an input. If the neuron has no variability, if the output of the neuron has no variability, we would be able to read out the variable with infinite precision. The reason why we are not able to do this is that there is variability and noise in the activity in the brain. As I mentioned already, plasticity, we will assume that it happens through changes its local plasticity rules, that the synapse knows about its own strength, it knows about the activity of the presynaptic and postsynaptic neurons, and this is what it has to work, maybe a teaching signal, this is what it has to work with in order to decide whether to be increased or decreased. And I already think I've mentioned this several times, we'll think about computation and learning as emergent phenomena. Okay, so and actually one more theme or tool that is very important, which I should have written here and I didn't, is how to deal with information. So we will talk in this course about information theory, which is provides us with important tools in order to think about information. Okay, here's a more detailed syllabus. I think that the syllabus is a bit too ambitious and I will not cover everything that is mentioned here, although in principle it's broken up to weeks and it all sums up to 14 weeks, but again, I think we will probably end up doing a bit less. So we will start with talking about neural decoding. So the point of view will be, suppose that we know something about how the neurons respond to a sensory variable, tuning curves of neurons in V1 or in head direction cells or whatever. How well can we read out the variable from the activity of the neurons? Okay? I think that I will not go through the detailed topics right now. I might or might not, I haven't decided yet, talk about this topic, which is a somewhat more technical topic, but it's somehow important when we really deal with real data or record or experiments. You stick an electrode, you provide some stimulus to the brain, and you measure the activity of a neuron. How do you use these measurements to characterize what this neuron is doing? What is its tuning curve? What is its receptive field? How do we define a receptive field? So I might talk about this topic. And then we come to a very important part of the course, which is reversing the perspective from the previous part. So the previous part, we asked, given that we know how a neuron represents information, how can we decode the variable from this information? And now we're going to ask, what are the principles that govern how the brain encodes information? Are there some reasons why the brain encodes information the way it does? And we will start with an important hypothesis called the efficient coding hypothesis, raised in the 60s by Horace Barlow. We will talk about that, and then we will talk in more detail about principles of coding. We will assume that the brain encodes information in an efficient manner. That's the efficient coding hypothesis, but we need to first formulate what we mean by this statement. And then this is another topic that I'm not sure we'll do. It depends on how fast we do the previous one. I want to talk a little bit about recurrent neural networks and how some forms of local plasticity rules can shape their structure. And finally, more or less the last 4 weeks of the course, we will talk about supervised learning and some basic concepts which I'm sure some of you have heard of, which are important: linear discrimination, the perceptron, support vector machines, and so on. Books. So I'll mention here 4 books, and there's a broader list on the Moodle page. This book is a very readable book by Peter Dayan and Larry Abbott, and it covers quite broadly many concepts in computational neuroscience, not in a lot of depth, but it's very readable, and it's a good way to get a broad picture of the field. And it does cover various topics that I will talk about. This book is more mathematical, more detailed. It's relevant to some of the topics that I will discuss. This book is not really very relevant directly to what I will do in this course. It's relevant to some of the parts about decoding, but it's just a nice book to look at. It's nicely written, and it's an inspiring book. And when in the second part of the course, when I will talk about principles of coding, and I will start with information theory, then this is a very standard textbook on information theory, and it could be useful for you. And as I mentioned, there are additional recommendations on the Moodle page. I will also try, as we go along in the course, to put on the Moodle page original articles related to things that I will teach. Many of the things that I will teach you were done a long time ago, going even up to the 60s. I mentioned Horace Barlow and his hypothesis of efficient coding. Some things were done in the 70s, some things were done in the 80s. And it's often nice to just look at the original papers. It gives some perspective. I find it always very interesting to see how, in some sense, our point of view has changed throughout the years, and in some senses, it's very, very similar today to what it was 50 years ago. Okay, this concludes the computer part. Any questions? Yes.
Could you give us an overview of the kinds of math that we should know before taking this course, and also specifically for the next few weeks, if there are some things that we should review
Yeah, I think Neta will talk with you about this more, but I would say the most important mathematical tools that you will need are probability and statistics, okay? That's crucial. And I know that this is, from last year, that this is, I think, the area where people had the most, some people had the most difficulty or holes or in the knowledge. So this is very important. And I encourage you to use the extra hour that Neta will give in order to not only, tell her about things that she knows more or less what you might be missing, but if there's something that you think that you need some more examples and explanations on, tell her, and even better, tell her in advance. And maybe this will be, I hope that this will be helpful. And then so probability and statistics, and the other topic is linear algebra, and I would say Fourier transforms. Fourier transforms will be important not now, but in the second part of the course, when we talk about neural coding and the retina, discrete Fourier transforms especially. I'm trying to figure out how to open the lights here. Tada. Thank you. Okay. Okay, we're done. I thought that I will start doing some things on the whiteboard, but this will be on Thursday.
טוב, נראה לי